tricuspid. And here's some representative images of ones from full-term pregnant cattle. So these are cattle at approximately 9 months pregnancy, similar gestation to ours. And you can see, you don't even need to measure this, you can see the incredible increase in size of all four valves from all four leaflets. The aortic valve leaflets nearly double in size. And this is remarkable given that this is something that happens over 9 months, that these leaflets double their size. Not only that though, their composition is completely changed. The proportion of elastin and collagen, remember I talked about the importance of those two components. So here, for instance, is the elastin content for the aortic valve, mitral valve, pulmonary, tricuspid. And I've got the elastin contents expressed as percentages of weight of the tissue. So, you know, I mentioned these are mostly collagen. You've got about 10% elastin in the aortic valve in non-pregnant animals. In animals at full term, the elastin content is cut in half or cut by more than half. And that happens across all of the leaflets. And we saw this with the other tissue components as well. Collagen content went up, elastin content went down, and the mechanical properties of the leaflet also changed. And without going through what these curves mean, these are tension aerial stretch curves similar to stress strain curves. So a valve leaflet from a non-pregnant animal would have a tension stretch curve that would look like this. In early pregnancy, the curve shifts to the left. This corresponds to the leaflet stiffening. And then in late pregnancy, the extensibility shifts back to its non-pregnant state. And this happens in all four heart valves. So what we have in heart valve remodeling is remarkable. The valves increase in size, completely change their composition and structure, but retain their original pre-pregnant mechanical properties. See how I'm doing for time here. I'm going to explain what happens to the aorta very briefly. I wanted to see what happened with the aorta. We expected to see something similar. We hypothesized that anyway. And the aorta was a particularly interesting question because the elastin in the aorta is supposed to be a protein that once it's laid down, it's never turned over, or basically once you reach maturity, the elastin gene is supposed to turn off and never turn on again. So the elastin you have, you know, at 18 years of age or whenever you stop growing is supposed to be the elastin you have for the rest of your life. So again, I had people telling me the aorta won't remodel because elastin can't remodel. And any widening that is seen in pregnancy can't involve the elastin. So again, I'm skipping forward here to my study of the aorta. We did the same structural and mechanical studies on the aorta from cattle throughout pregnancy. And again, we saw this change in mechanical properties, although this time it went the other way. In early pregnancy, the aorta becomes more extensible, and then that reverse extensibility is reversed in late pregnancy. So again, the aorta ends up with mechanical properties identical to that in non-pregnant animals. But all the while it's doing this, it's increasing in size, as we've seen in humans. And if we look at the structure, it's increasing its elastin content by over 50%. And you can even see that in these cross sections. All of these wavy fibers that you see in the non-pregnant aorta, these are elastic fibers that you see on cross section. So this is the aortic tube cut in cross section. And in early pregnancy, it looks like that elastin fragments, becomes cut up in little pieces almost. And then this could be part in what allows the aorta to expand in size. And then in late pregnancy, that elastin is resynthesized and those fibers are reinforced. So like the heart valves, the aorta increases in size, changes its composition, changes the structural arrangements, but retains the mechanical properties of the tissue from its pre-pregnant state. So taking all these studies together, this is our model of cardiovascular remodeling during pregnancy. It's a biphasic or two-phase remodeling mechanism. And this is my, if you just look at the diagram here, here's my diagram of the crimped collagen and elastic fibers that you'd see in the tissue. So in non-pregnant conditions, you would have your elastin and collagen fibers with your cells that maintain those structures. In early pregnancy, you have volume overload, the aorta gets wider, the heart valves expand, and the elastin and collagen become straightened. And that straightening out pulls on those cells and triggers those cells to turn on their remodeling machinery. And those cells synthesize more collagen or more elastin and remodels the structure of that throughout the tissue, adding more collagen and more elastin to make the tissue larger, but also changing the proportions and their interconnections. So you end up with a material that mechanically behaves the same as it did in the non-pregnant state, but a tissue that's much larger and has a completely different structure. Why is this happening? This obviously is all to serve to maintain cardiovascular function in the maternal circulation during this volume loading of pregnancy. The question I'm always asked, are these changes reversible? And so very quickly, I collected samples again from never pregnant cattle and cattle that have been previously pregnant. And by comparing these, I can see what are the effects of pregnancy on these structures. Comparing previously pregnant to never pregnant is going to tell me, are the structural adaptations that happen during pregnancy, are they reversible? And if you look at the data here, you can see the heart mass is larger in animals that had been pregnant. The heart volume is larger. The aorta remains wider. The aorta contains nearly double the amount of elastin, and the aortic valve, the valve leaflets remain enlarged. So my interpretation from this, at least in cattle, are all these changes that happen in pregnancy are not reversed postpartum. Questions that remain. Are there additional triggers for cardiovascular adaptations? This is where my knowledge starts to run out. People ask me, well, what are the triggers for these adaptations? And beyond the volume overload and the hormonal triggers, I'm not absolutely sure. But it's something that makes this adaptation so different from pathological remodeling. If we look at the mitral valve, for instance, in pregnancy, we saw the leaflet gets bigger, it grows more chordae tendineae, it changes its mechanical properties and structure to function properly during this volume overload of pregnancy. If you take a heart valve in heart failure, a mitral valve in heart failure, it sees the same volume overload, but for some reason it structurally deteriorates and sometimes fails and has to be replaced with an artificial heart valve. So what is the difference between heart failure and pregnancy? It's the signaling received by those cells. Something in pregnancy is telling those cells, rebuild the mitral valve in this way to make it beneficial. And if we can understand what those signals are, maybe we could harness those signals and translate that into a clinical treatment. And when I look at what some of those other possible triggers could be, what else could be driving this adaptation in pregnancy, other than just mechanical overload or maybe hormones. And I found this study, and this is a study that showed they looked for an explanation as to why pregnant women recovered from heart attacks faster than other patients. And the researchers had a hypothesis that there was something coming from the fetus, the placenta, that helped to repair a maternal heart attack. So they did this study in mice, and basically they injected this fluorescent green protein in the embryonic mice and induced a heart attack in the maternal mouse. And what they found was fetal stem cells left the fetal mouse, crossed into the maternal circulation, localized in the mother's infarcted area of the heart, and those stem cells repaired the infarct. And so this is called fetal stem cell transfer. And there's evidence of fetal cells leaving and entering the maternal body in almost all tissues. And so, you know, the explanation here was, well, this makes sense because this is an evolutionary adaptation for the fetus to reach full term. If the mother has a heart attack, the fetus is going to send stem cells, go in and repair the maternal heart because we need to get to full term. And so that makes complete sense. Well, my wondering is, could it be possible that fetal stem cells also traffic into the maternal cardiovascular tissues to help drive this adaptation to pregnancy? And so I saw somebody put a astonishment emoji here. I put that plus an alien emoji because it is a little bit disturbing that cells from the fetus can cross into the maternal body and repair something. And just as a note, those fetal stem cells do stay in the maternal body for their lifetime. So again, why is this important? Why do we care about pregnancy adaptations, cardiovascular adaptations in pregnancy? We've seen in both the heart and in heart valves and now in aorta. There's some smart material, beneficial adaptations, remodeling that happens in pregnancy that is distinct from pathologies. And if we can understand the processes driving this remodeling during pregnancy, then maybe we can harness those for clinical treatments or even for tissue engineering techniques for growing replacement heart valves and arteries. So I'm sorry if I've gone a little bit over time, but that's where we are at the moment, and I'm very happy to answer any questions.